So we decided to maximize this log likelihood of the model, given the this model has some parameters, theta, and I have to find the optimum theta such that it's maximized. So basically, I can take the derivative of log likelihood with respect to these parameters, and parameters are Vm and Vc, and I take derivative with respect, say, of Vm. Sorry, Vw. Okay, this is going to be summation over all W of derivative of log of this P. Okay, when this P is log of e to the power of Vw transpose Vc, right? Divide by summation over all W prime of e Vw prime transpose Vc. So I need to take derivative of this. So maybe we apply this W with this log first. So this is going to be, if I apply this log, so I have summation over all W. Log of e to the power of Vm transpose Vc would be just Vm transpose Vc minus log of sigma over W prime e to the power of V transpose W prime Vc. Okay. So now I can take the log. So log of log likelihood with respect, say, to Vw is sum over W. So derivative of Vw transpose Vc with respect to Vw is what? Vw transpose Vc derivative with respect to Vw. It's just Vc, right? So derivative of this log, I mean Vw transpose Vc is a scalar because it's dot product of two vectors. You take derivative with respect to a vector. The derivative is going to be a vector. Derivative of a scalar with respect to a vector is a vector, right? Because that's what derivative means. You perturb something, you know, the derivative of this object with respect to this. I perturb this, how much this will change. I have a scalar, take derivative with respect to a vector. Each element of this vector will be perturbed. This is going to change. So it's a vector, which gives me direction of change. So the first term would be this vector minus derivative of this log, which is going to be 1 over this value times so I have derivative of this with respect to Vw. You know what this summation is? You know, this summation is over all W's, right? And I have dw's because that's the size of vocabulary. This is basically e to the power of v transpose 1 vc plus e to the power of v2 vc. At some point, this index is going to be w, the same as this index. And then some other terms, EVD transpose VC. Now I want to take derivative of this with respect to Vm. All of these terms are going to be 0 except this one, right? And this term, the derivative of this term, is going to be e to the power of Vm transpose, this is Vw, sorry, Vw transpose Vc times Vc. Okay, that's the derivative. Now look at this quantity. It's familiar quantity, right? E to the power of WVC divided by the summation over all. This is yi, or this probability, right? So basically, derivative of log likelihood with respect to Vw is going to be summation over all W of Vc minus, this is probability of W given C, this quantity, times Vc. So this is W, I take this factor Vc times 1 minus P Wc. Okay. That's the derivative of log likelihood with respect to Vw. Now if I want to do gradient descent, if I want to do gradient descent, I can initialize Vw and then set Vw new is Vw old minus some learning rate times Vc one minus P Wc. So I can initialize with some Vm, Vw, and Vc and apply gradient descent to find Vw. I can exactly do the same thing, take here derivative, instead of taking derivative with respect to Vw, I can take derivative with respect to Vc and write a function for Vc. You know, there will be a term here. And I can initialize this with some term and then, keep going until it converges. If you look at this update formula, it's pretty meaningful. I mean, you can interpret it pretty nicely. I initialize a VW. I have a vector representation for word W, either as initialization or is one of the result of one of these iterations. Now suppose that probability of observing this W given context is high. So having this V, C, and VW, I can compute a large probability. Say it's 1. If I compute a large probability, this is going to be 0, and I have no update. That's a good VW. It's a good VW. But if it's not large, if it's a small, then a proportion of Vc will be subtracted from Vm. Okay? Means that make VM closer to VC. If you can predict it well, we are done. If you can't predict it well, make these two vectors closer. That's basically what this update function does until it converges. Okay? So if you have been careful enough, you notice that we have two set of vectors, set of vectors VW and set of vectors VC. When C represent context and W represent the word. But set of all words and set of all contexts are the same, right? Any word can appear as a word or can appear as the context of this word because, if you have a window, you go over all of them. But end of the day, you have two set of different vectors. You have a set for VM, you have a set VW, and you have a set for VC. You have two different sets. And that's exactly what Word2vec does. Word2vec generates two sets of vectors. Basically, for each single word, you have two vectors. One vector represents this word when this word is in the place of context, and one vector represents this word when this word is in the place of central word. Okay. And why is that? Why do we need actually to model basically have this type of modeling instead of having one single representation for each word? Any idea that, any motivation that why we need two set of vectors? That's actually one motivation could be this, that, yes? Mm-hmm. One thing that I forgot to mention, and it made some confusion, is that, this VC and VW was rows and columns of W and W transpose. Basically, they were weights of the neural network that we wanted to learn. But Word2vec treat them as as a vector representation of the words. I mean, what is the output of Word2vec is basically these weights of the neural network. Each of these weights is a vector representation of one word. Okay. Yeah, but intrinsically in this model, we need to have two sets of weights. But the consequence of this is that we have two sets of representation for words, which is not clear. Why do we need that? And I was asking any motivation. One motivation could be, which I'm not sure actually it's necessary. I think it might be possible to model the vector representation in a way that we don't need that. But one motivation could be, suppose that you want to compute the probability of one word given the same word. Okay, what's the probability of book given book? Means what's the chance that this word book appears right after word book? It's very low probability. It's very unlikely that you repeat a word after itself, right? But suppose that you don't have two different sets of vectors, you have one set of vectors, then this is going to be e to the power of VW transpose VW. And no way you can make this probability as small, because that's the largest value possible for any vector. So the probability of appearing a word after itself would be large. You don't want it. And maybe that's one of the motivation to have two different set of words. And then you have to take care of that afterward, because at the end of the day, either they take average of these two sets, or they just add them up, or they concatenate them. There are different variations. Okay, so we have basically, this for this simple model of continuous bag of words. So I can relax this assumption that the length of the context was 1. And I can make a neural network, that was my neural network that, I had this D dimension, and I had this H as hidden vector, and I had another D dimension, okay? That was one of the context words, and that was the central word that you wanted to predict. So if I relax this assumption that the length of the context is 1, then instead of one word, I have a couple of words here. But all of these couple of words, can share the same set of weights. So in the first step that we had H transpose H being W transpose X, now we have W transpose like X1 plus X2 plus X3, depends on how many words you have in the context. Okay? So you can extend this model to the case that it's not as simple as one word. Length is more. And basically almost everything else would follow exactly the same. You can have exactly the same model and take derivative and set it to 0 and so on. Yes?
I had a question about the summation index there. Yeah. Shouldn't that summation go away because we're taking the derivative with respect to just one dw?
Sorry, which part?
Well, I mean, so in the first line of the second board, we have del L by del VW. First line?
Yeah.
And then the summation is overall.
Yeah, sorry. Yes. Yes. Yeah, and we don't have it here actually, with mistake. Yeah, it's with one of these words. Yeah, thank you for mentioning this. There is no summation here. We are talking about one of these words. Everything else will be Z. Okay, so you can extend continuous backup word this way, and you can. That's continuous backup word. You can do it this way. You can do exactly the same thing with a skip-gram model. Then the difference is that this you have one word and you have this hidden word H, and here you have a couple of these words. That's not going to be much different from this derivation, and you can do it almost the same as this one with a slight modification and compute the derivative and so on. Okay, that will be a skip-gram. This one was continuous backup word. However, in software of Word2vec, that's not the optimization that they're doing. This optimization for large corpus is intractable. You can't do it in practice. And the reason is this normalization factor. In each iteration, you need to compute this P. To compute this P, you need to compute this normalization factor. And this normalization factor is a summation over all words in the vocabulary. And when the corpus is large, all words are in the vocabulary is really large. And so it takes so much time in each iteration to compute this sum. So that's basically not what has been, what is used in practice. What's used in practice is what they call it negative sampling. Okay. So negative sampling is basically a completely different objective function. They don't optimize this objective function. That's the second paper, which skip-gram has been explained as the continuous backup word and the objective function that they use. Okay. Unfortunately, none of these things are quite clear in the paper that this is an objective function that is different from the previous one. It's not the same objective function, or even how this objective function has been derived. But the idea, which is pretty nice idea in the second version, which is negative sampling, is to come up with a different objective function and get rid of this and treat the problem completely differently based on the assumption that we are doing a classification problem. So just suppose that I'm doing a classification problem and I make pairs of words and context. I make a set D such that D is set of all WC pairs in the text. So I have this windows with some length, and I look at my whole corpus, and whenever a word and its context appears, I mean another word as a is in the context of that word, they appear together, I put this pair in set D. Okay? Now assume that I have another set D prime, which is set of the set of all pairs that are not in the corpus. So you may think that we don't have D prime, but for the moment assume that we do. Okay, so you have the text. In the text you can see that pairs that comes together and put them in a set. Now assume that somehow I have another set that shows pairs that are not coming together in my text, in my corpus. Okay, so that's D prime. Now I treat the problem as a classification problem. So I have two classes. Class of pairs that are in the corpus and pairs that are not. So suppose that I want to do classification. I want to give a pair to my classifier, and my classifier should assign a label to it. 1 means it is in the corpus. 0 means it's not in the corpus. Okay? So Z equal to 1 means D is in the corpus. So let me put it this way. So probability that Z is equal to 1 given this pair represent the probability that W and C is in the corpus. And probability that Z is equal to 0 given WC means the probability that it's not in the corpus, means it's in D prime. Okay, now assume that it's a classification problem and solve this classification problem using logistic regression. Okay. How many of you have seen logistic regression before? Okay. So I don't need to explain logistic regression then. No, I mean the details of logistic regression. It doesn't matter actually that, because many people use logistic regression, but they haven't seen the derivation of logistic regression. But anyway, you know, I can assume that each of these probabilities can be represented by a logistic function. You know, I can say that, okay, probability that Z is equal to 1 given this pair is 1 over 1 plus e to the power of VC transpose VW. So I represent these two words by two vectors, and this is basically a logistic function which represents this probability. And I can present the probabilities at 0 given WC as complement of this, 1 minus this, right? which is going to be e to the power of minus VC transpose VW1 plus e to the power of VC transpose VW, right? Yes?
What's VC and VW?
Vector representation of word V and vector representation of word C. So I have a pair that is in the corpus. I have a pair that's not in the corpus. When I train my classifier, I need to represent this word somehow. I represent this word with a vector which is unknown to me at the moment.
This isn't a binary vector, though.
Sorry?
This isn't one of the binary vectors.
No, it's unknown vector. It's exactly the same as vectors that we had in the past. It's some vector in p-dimensional space that I don't know the value of that vector. This is unknown of the model. I want to learn this vector. I want to compute this vector. It's a parameter of my model. So this is complement of this one. To come up with the formula that it's in the paper. So let's write this complement. Let's multiply this by e to the power of VC transpose VM, divide by e to the power of VC transpose VM. So if I multiply this by e to the power of VC VM, this is going to be 1, right? And denominator, I multiply everything by this. This term is going to be e to the power of VC VM. This term is going to be 1. So it's going to be 1 plus e to the power of VC transpose VM, VW. I should have called this VM because the number of times that by mistake I put M is really more than the number of times that I do it correctly, doubly. Okay, so this is the complement of this one. And now I can model the whole probability, the joint, the whole distribution as 1 divided by 1 plus e to the power of negative VC transpose VW, okay, to the power of Z times 1 plus e to the power of VC transpose VM, 1 minus Z. That's probability of observing Z given W and C. And now WC and WM are unknown. If Z is 1, I only have this part and this is 0. And if Z is 0, I only have this part and this is 0. So this can represent the probability of, or the distribution of both classes, negative and, 0 and 1 class, being in the corpus or not being in the corpus. So I have this probability. I basically model this posterior probability, and these are parameters of my model. So I would like to learn these parameters. How can I do this? Again, I can do maximum likelihood estimation, right? So if I do maximum likelihood estimation, then the likelihood of this model is going to be pi over this whole quantity or let me write it more nicely. I just write it pz given wc over all pairs wc that are either in D or in D prime. That's my likelihood. I can take log of this. So log likelihood, and theta is again VC and VW. Log likelihood would be summation over all pairs that are either in D or D prime. And then I have Z times log of 1 over 1 plus e to the power of minus VC VW, right? Plus 1 minus Z log 1 over 1 plus e to the power of VC transpose VW. Okay. This is for all pairs either in D or D prime. When they are in D, Z is 1. So this part is 0. When they are in D prime, Z is 0. So this part is 0 and this part is non-zero, right? So I can write it in this form. I can put a summation here and say that this is over all pairs in D. And I don't need this Z and Z minus 1 anymore. This is all pairs in D, and this is all pairs in D prime. Okay? And get rid of this Z. Now take derivative of L with respect to one of these parameters. Say, take derivative with respect to Vm, Vw. Okay? Take derivative with respect to Vw. It's going to be summation of pairs in D, and then you can take derivative of this log, which is clear how to do it, and to take derivative of this log, which is clear how to do it, and then you can do gradient descent using this basically update function now. See, I don't have this problem of summing over all possible words, which made the previous update intractable. I don't have this problem anymore. So, and this is basically my objective function. This objective function is called negative sampling objective function, okay? With a little bit difference that I'm going to show you in a slide. Any question here? It needs a magic hand.
So basically, we're trying to learn these VC and VW from the data itself.
Yes.
Right? As we are getting new sentences, we are kind of updating our knowledge about the VC.
Yeah. Yes.
So at the output layer, we used to have only one output, like z equals 0 or z equals 1, or
This is a classifier.
so one output at the end.
Yeah, it's just logistic regression when you treat your data in two ways. Either this pair is in the corpus or this pair is not in the corpus.
So we don't have y, yi, like before.
No,
So different neural network.
it's completely different objective function. Different. It's not a neural network anymore, because neural network is a couple of these logistic regression on the top of each other, right? It's not even a neural network anymore. It's just yes.
So this Word2vec representation where you have inputs and some, hidden, and then the output layer with the same number of neurons as input, is it not something similar to like autoencoder kind of thing where you're kind of trying to reconstruct in some sense of that, right?
So that's a very good point. That's a very good point. You are familiar with like PCA and dimensionality reduction. How do we do dimensionality reduction using neural network? They do it through autoencoder. An autoencoder is basically a bottleneck. I have this X as input, and then I have usually a couple of layers, and then I have a layer at the middle, and then I reverse, this number of layers to get to same dimensionality. The input of the vector is X, and the output of the vector is X. So I give X to the vector. I want to construct X. Through this, construction of X through these weights, I go through this bottleneck. And this is basically my low-dimensional representation of the data. And you can prove mathematically that if you have a linear autoencoder, the basis here is exactly the same as basis of PCA. So it's exactly find the same basis. Okay, but you can have deep autoencoder. You can have many of these layers, and it can lead to nonlinearity. But the thing is that this basically does dimensionality reduction for you, or manifold learning for you. So remember when we started this lecture, we started that with the concept that you have term frequency matrix or co-occurrence matrix, and then you are going to use SVD, singular value decomposition, to do dimensionality reduction, or other techniques for dimensionality reduction, LSI, and so on. If you want to do dimensionality reduction using neural network, you need this type of bottlenecks. And you are completely right. What this Word2vec conceptually does is to take all of these words, go through a bottleneck, and come back reconstruct it. But it doesn't reconstruct the same word. It doesn't reconstruct the same word. It reconstructs the consequent word. But it reconstructs the words around this word. But still, it goes through this bottleneck, and it has exactly this sense of dimensionality reduction. My plan was to introduce a couple of projects based on this, which you can choose as your final project. And one of them, remind me afterward if I forget, that is based on this understanding of this autoencoder and the relation with PCA. We know PCA, if this is X, this is X, is identical to this, not identical, find the same weights as this linear autoencoder. Now, if instead of this X, I have consequent X in neural network, what would be the corresponding method in, SVD type of models? If I can write it in linear algebra form, I think you can write it in a very good form, and you can solve it in closed form. It may not be as good as Word2vec, because they have many heuristics that I'm going to show you, but it's possible, most likely. Okay, so that was the two models that we discussed, and we realized that it's intractable, and then a skipgram should be solved using negative sampling. This is the final formula that they have in their paper for negative sampling, except that we did it over all pairs on the corpus, and they write it for one single word. So that's one term of this summation. And for this one single, they have this notation of this. We have VC and we have VW. They have VWO prime and VWI prime, and I is input and O is output, and W is word, and prime is like our C, and no prime is like our W. So that's basically, this is a logistic function. This is, exactly the same logistic function of either VC, VW, or negative of that one. Okay, I think there's a mistake here. There should be a negative sign here. Okay. One of the other difference in their objective function with what I did here, because they don't explain it, it's the logistic regression, they come explain it intuitively, is that for every single word, they have a summation of k words which is not in the corpus. So they do it for one pair. The first one pair is this term plus k words that is not in the corpus. For every pair that is in the corpus, they want k pairs that is not in the corpus. If you maximize this objective function, basically you are maximizing the possibility of word being in the corpus and minimizing the possibility of word not being in the corpus. They are maximizing the possibility of word being in the corpus, and they are minimizing the possibility of k words not being in the corpus. Okay, why they are doing this? It's completely heuristic. They tried many different things, and it turned out to be better. And intuitively, it makes sense, because I'm going to tell you how they generate these words that are not in the corpus, and it makes sense that you need more than one of them. The way that they generate these words that are not in the corpus, because the pairs that are in the corpus is clear. How do we generate words that are not in the corpus? We have a probability of basically unigram of words. For each single word, I can count the number of words, the frequency of word, divided by the total number of words. That's my unigram distribution of words in the corpus. What they do is that given a word, suppose that I have this WC in the corpus. So given a W, given a context in here, I'm going to sample a word from this unigram distribution. That is going to be a random word. If I tell you a word and you randomly tell me another word, most likely it's not in the corpus. They treat that as a word here. Sampled from this distribution. This distribution is a unigram of words. So why they have k of them? Because, I told you how it has been generated. I give you a word, and you randomly choose from one of the words in the vocabulary with the hope that since I chose this randomly, it shouldn't appear together. But there's a chance that it does, right? So I repeated k times. K repetition, I choose a word to make sure that, the chance that, all of these k word that has been selected randomly or as a pair in the corpus is not really high, okay?
Average it out as well, or just?
That's exactly what they do. This one term plus k of these. You weight. The weight of that part is more. It's like having an imbalance problem for classification.
Mm-hmm,
When you need to, sample more points from one class. Okay, another thing that they do is to, this is unigram distribution of words in the corpus. Another thing that they do is to, instead of sampling from p, they sample from p to the power of t over 4. Again, there is no mathematical justification for what they are doing. It's just another heuristic. They realize that it works better this way. But one motivation or one intuition behind this is that assume that the frequency of some of the words are really small here in p. If you have a very small number up to the power of t over 4, it's going to be larger. So the chance of sampling from less frequent word is more. That could be a motivation, but many other numbers other than 3 over 4 do the same job, but it turned out that 3 over 4 works better, and they picked that one. And when they learn this word, they just add them up. I mean, they have a set of words set of vectors for words, set of vectors for context. They just add them up. They'll take the average, or they concatenate them. There are different ways of doing this. The problem eventually was, negative sampling eventually was logistic regression. We saw that, right? But the difference is that in logistic regression, your input is like x, and here you have a beta, which you have to learn is direction of your decision boundary. And the problem is convex. So basically, you can find the global minimum. And we can have the second derivative, use Newton-Raphson method, for example, and do it pretty quickly. Here, because it's by convex problem. Together, VC and VM is not convex. Given VC is fixed, it's convex on VW. Given that VW is fixed, it's convex on VC, but it's not convex on both variables. So again, when we talk about project, this fact suggests that you might be able to do better in terms of optimization. We will talk about it later. Okay, here is some examples that they show. Besides those two relations that I showed you, for example, the relation city and state, for example. If you tell the algorithm, or you have some vectors, and basically you would like to see the relation between Chicago to Illinois, if you know this relation, then which vector has the same relation with Houston, and that would be Texas. Basically, it kind of find you, this last word here. It's like Chicago minus Illinois plus Houston is equal to Texas. Okay, so these pair have the same relation as these two pairs. Okay, so Chicago to Illinois is like Philadelphia to Pennsylvania. And so you can basically infer some city in a state, and you can do the same thing with capital and word like different countries and their capital. On the relation between bad and worse is the same as the relation between big and biggest, or between bright and brightest and cold and coldest. All of these vectors have the same distance. The distance between bad and worse is the same as distance between bright and brightest. So basically, if you add this distance between bad and worse to bright, you get to brightness. Okay? And like past tense, the distance between dancing and danced is the same as dancing and decreasing and decreased, and so on. So you can imagine how useful it's going to be in natural language processing. It is, in fact, having this word representation is quite useful. And they computed this word vectors, and it's like a dictionary that you can even use it and, Like for each, this word, they run it on a very large corpus. You need to have very large corpus, otherwise it's not going to work well. You need a huge corpus to train the model. Otherwise it's not going to work, yes.
And these data sets, gram 7 past tense,
Right.
are they training just grammar here?
No, the training for all of these would be just this.
No, sorry, I realized that, but were they, like, this corpus, would it have had, say, non-verbs, is what I'm asking? Would
Yes,
they have
yes,
verbs?
yeah.
King, queen, and
Yeah.
that?
In the same corpus, you choose these verbs, and this is the relation. And there are many non-verbs in this corpus. It's like raw text, almost the whole internet, This data set is basically text of almost the whole internet that has been trained on. It's huge. Yes?
So over here, what we're doing is we're trying to represent a word with two vectors, right?
Mm-hmm.
What about like generalizing it further to find out deeper patterns? Maybe?
Sorry, generalizing to?
Generalizing it further, for example, representing words in, let's say, three vectors, using three vectors or something.
Why is it good for? Why do we want to do that?
So here is it's a very simple relation that we're trying to figure out.
Mm-hmm.
I was just saying maybe.
Oh, here you mean instead of two vectors, we have more than?
Yeah, I mean.
Oh, not in the term of learning.
Yeah.
Or learning, you're
No,
saying?
the representation, the very
Mm-hmm.
representation. We said VC and VW.
Okay, yeah.
But instead of just two vectors, we have like more vectors there.
No, even, these two vectors, we have to take care of that and make it one representation for each word. As I said, at the end of the day, I need to add them up or concatenate them and say, okay, this is my representation for a word.
Sure.
You don't need more than two, and even it was not quite clear that why do we need two at the beginning, and I gave you an example that it could be useful to have two.
Yeah,
But I don't see why we need more than two. Because here, don't get confused that this one of them is not VW, the other one VC. VW and VC are combined, and you have a V for each vector. I mean, it's a good point, but if you think about this algorithm, never in the process of this algorithm, we had any indication that at the end of the day, we have this property of adding and subtracting vector and get this result. The only thing was that semantically close words appear close to each other, and then it gives you such properties, that their distance is meaningful, okay? So you have a good point that there might be some nonlinear relation between words, or we might be able to map the word in a space such that there is some nonlinear relation between them. That's quite possible, not just adding and subtracting, but more complicated functions between them, and we infer something. Does it exist here? We don't know. Is there a method that we can map the data in a low-dimensional space such that it has this type of property? Again, we don't know. I mean, I repeat that we never, wanted this method to do this. Yeah, it just happened that, not just happened. What happened is that this model, the only thing that this model requires is that a word which surrounding word that have basically the same meaning, supposedly, appear close to each other in this vector space. And this is a consequence of this, right? Which has been just demoed and presented very nicely. All papers before that, they just had a two-dimensional map and said that, okay, see, these are close to each other. Okay, there is another paper in 2014, Glove, which is not as famous as Word2vec, but it is pretty famous paper and famous model. And there are claims from both sides. There are claims that GloVe is as good as Word2vec in the original paper. There are claims that people said that they were not able to reproduce the exact result. It's not as good as Word2vec. But anyway, one fact about GloVe is that it can be run on corpus with a smaller size compared to Word2vec. Okay, and GloVe is very simple. Remember this Word2vec, this co-occurrence matrix that we had? GloVe is just matrix decomposition on co-occurrence matrix. But in fact, it is matrix decomposition not only on not on the original matrix, not original co-occurrence matrix, but on the log of this co-occurrence matrix. So suppose that you have co-occurrence matrix, you take the log of that and you do matrix decomposition. That's GloVe. Okay, so GloVe basically assume that Vi times Vj, or these two vectors Vc times Vw, Vc transpose times Vc, is one of the entries of this matrix. So if you decompose this matrix, you're going to find these vectors. Okay. Again, there are some heuristic involved here, like this function which has been multiplied to this log. And this function, what this function does is to somehow put a cap on very frequent words. This function is like this. There are some words that are very frequent, like articles, A, D, but they are not that representative. D is everywhere, A is everywhere. You want to put a cap on this, the appearance of this word. And that's what this function basically does, somehow weights these pairs. Another thing is that you can have this log of co-occurrence matrix, and for matrix decomposition, you can do singular value decomposition on that. But this is going to be computationally intensive and has the drawback that we had mentioned at the beginning. So they don't do decomposition using singular value decomposition, for example. They do it using gradient descent. You have closed form solution here, which you can apply, singular value decomposition. But they don't use this closed form solution, and they do gradient descent. So they basically write the objective function for every single element of this matrix. So every single element of this matrix should be Wi transpose Wj. And they do gradient descent to solve this. Interestingly, when they apply this function, they have another heuristic that what would be the power of this function. If you look at the detail, and at the end of the day, the power is 3/4, same as the power that we had in Word2vec. Okay, so we are done with Word2vec and with GloVe. But now I want to show you some connection, because Word2vec and many other algorithms in the literature of neural network are motivated by the fact that matrix decomposition is hard computationally, and it doesn't basically provide satisfactory result. Never LSI was as good as this, and so on. But there's a paper, not this paper, sorry, it's a pretty old paper. I maybe forgot to put the paper here. No, this paper. There is this paper in 2013, which they prove Word2vec is identical to a matrix decomposition. And I want to show you the flavor of this basically claim and proof. We have this concept, point mutual information, PMI, and point mutual information between W and Wj is defined as log of joint probability divided by marginal probability of each. Okay. Now, if you want to apply this to, a corpus of words, basically an estimation of joint probability of Wi and Wj, if W is a word and Wj is a word, is just the number of times that these words appears together divided by the total number of the word in that corpus, right? And P of Wi would be the number of W's divided by total number. And P of Wj would be the number of all Wj's in the corpus divided by the total number. So each of these quantities can be estimated in the corpus just by counting the number of words, right? So we can compute this quantity in a corpus. This PMI could be, in fact, negative, because it's a log of this quantity and could be negative. And this is one example, and if there is a pair that is not in the corpus, then this PMI would go to negative infinity. And if it's very rare, it's going to be a large negative number, because you can see why it's going to happen, because you're going to have log of 0 end of the day here. It's 0, you have log of 0 and it's negative infinity. So to fix this, there is another quantity which is positive PMI, positive pairwise mutual information, which is simply max of PMI and 0. So anything which is 0, negative, just set it to 0. This is called PPMI. Okay. Now look at the objective function that we optimized in Word2vec. Okay. Let me find this equation in favor of time. I have two vectors, Wi and U. We changed the notation here. I mean, this is the notation of this paper. I didn't change the notation. I can say that I was lazy, I didn't change the notation, or I can say that I intentionally put different notation for you to get familiar with different notations, different papers in the literature. So, but the truth was the first one. So I have two vectors, WC or WM or V and U or whatever. So multiplication of these two vectors, I define a new variable, x. Okay? Okay, if I define a new variable, and then, in favor of time, I skip all of these details, but just I tell you that if I put these two variables together as one variable, I call this x. Vc times Vm is x. And then I write my objective function. And whenever I need a probability, I use this estimation by counting the word. I'm going to have, and then take the derivative. I want to set it to 0. I want to optimize it. Take the derivative and set it to 0. Then over x, I have a quadratic function which I can solve in closed form. And this quadratic function that I solve in closed form has two answers. One of them is invalid, and the other one, which is valid, is this. So basically, this e to the power of x optimize my objective function. You can prove that. And x was vi times vj. If I show you that e to the power of x equal to this, optimize my objective function that I had in negative sampling, then if I take a log of these, x is going to be log of this quantity, and x was wi times wj. It means that if I decompose a matrix such that the entries of the matrix are these, then I will get wi and wj, which minimize this objective function. And this quantity is basically the log of PMI up to a constant. So the bottom line is that if you compute PMI, actually PPMI, take the log, do matrix decomposition on that, the result that you are going to get as vectors are the result which minimize the objective function of Word2vec, I mean negative sampling, a skip graph. Okay, so they're identical. And this is the topic of next lecture, restricted Boltzmann machine. But next week, we are going to have a guest lecture. Pascal Poupard from CS department is going to give a lecture on sum product networks. I don't know if you're familiar with sum product networks or not. It was a model, a relatively very new model, which basically, you know, it's a sort of probabilistic model that inference is exact in it, you know, because one of the problems with our probabilistic models is that most of them are intractable and we need all sort of approximation to solve that. But some products are exact, you know, we can do all type of inference in some product networks exact. And when it was published, the title of paper suggested that it's a new deep model because it's different layers of these variables. And at that time, basically, we had the notion of deep graphical models and deep belief network, which is less favorable now compared to that time. You know, now convolutional net and this type of models are more favorable. But anyway, that was suggested to the literature as a new deep structure. There is some sort of controversy around that in a sense that, you know, they are not, these two do not belong to the same camp. I mean, there's one camp which represent deep network as deep neural network or deep Boltzmann machine. And there's another camp which represents some product network as deep structure. So that would be basically a lecture on some product network. Then after that, we get to deep Boltzmann machine and convolutional network for basically the week which comes after we cover Boltzmann machine and convolutional net. Any question? Yes? No, if you reconstruct the original word, it's going to be LSI.
Okay.
You know, if you make autoencoder that reconstruct the original word, that's LSI.
Okay.
Because you can show that a linear autoencoder find the same basis as PCA. And LSI is PCA except that it's not centralized. Okay? So if you have a bottleneck such that the output is the same as input, that's LSI. But if you have a bottleneck such that the output is not the same as input but is surrounding word, that's going to be Word2vec. So that's one way of seeing the difference between LSI, latent semantic indexing or analysis, and Word2vec.
And how's this difference is coming? Is it because of the objective function that we are?
Yeah, we have different models and we have different objective function. You know, one of the point that I had, you know, I plan to discuss, you know, like 5-6 different projects as potential project, which I'm going to do in the next lecture. But one of my point was that, you know, you can see this sort of analogy. You know, you have this notion of linear autoencoder, which can be generalized when the output is surrounding word instead of the word itself. Now, on another direction, this linear autoencoder is similar to LSI. What this structure would be similar to, you know? Can I model this using this just linear algebra and do some sort of matrix decomposition which leads to this? I think you can. It's not, not that I have the solution, but I think it's a pretty clear direction that we can discuss. Okay, any other question? Yes?
Just about scheduling and the makeup lecture?
Scheduling the makeup lecture, yes.
Yeah, I think we can also schedule it before we start doing presentations.
It depends on, you know, because it's like a 3 hours chunk. I don't know how is your schedule. You know, it's pretty hard to find a schedule which fits everyone. I need to check this with scheduling rather than asking you, because if I have the list of everyone in the class, then scheduling can find me the, you know, a time which is has least conflict with everyone. I'm going to find that basically that slot and then let you know. Yeah. Okay. Okay, have a good Thanksgiving and